Yeah, hello everyone. I hope you can hear me and see my screen.
Yes.
Okay, perfect. I'm very happy to present here today. My name is Walther. I'm the head of the group on operations management at RWTH Aachen University. And I will talk about international supply chain and network design and national infrastructure planning for a hydrogen economy today. So I think the background, we already talked about that a lot already. We need trade in the future. We have high renewable potential countries and we have high demand countries, and that do not really fit spatially. It will need very high investments for infrastructures in the future. And we learned in the past, especially 3 years, that we really have to avoid disruptions in energy supply chains. So this is very important. And we will need transportation, international and national level. And there was also fluctuations in renewable energy. So that was the background where we started our research. And we asked ourselves 2 questions, or had 2 planning tasks. The first is, we wanted to think about methodologies for the design of international supply networks, balancing not only costs, which is often talked about, but also supply security risks. We heard this morning that it is not sufficient to have plenty of renewables. We also need very, very stable surroundings and situation. That was our first task, so that's the international supply. And then when we look at Europe, or for instance Germany, at our national infrastructure, we will also need hydrogen transport, but we have to regard for seasonal fluctuations, and there is storage needs. So these are the 2 topics that I want to talk about in the next minutes. Do you see an overview?
Sorry to interrupt. You have not a presentation mode view. Maybe if it's easy to change.
Let's. Is that better now?
No, we just see like the slides where you prepare the slides.
Yeah.
I
understand it. Because then we have to. Yeah, the presentation mode, which I don't see.
Hi, Grit. So if you go again to where you were before,
yeah,
and I can guide you.
I was in the presentation mode, but
yeah,
it doesn't. Yeah, okay.
If you could share again your screen.
Yes. Doesn't work. I don't see you. I cannot share currently because I don't get a large screen. Close this. No.
If you go on the top right corner next to the leave button, there is a share option.
Yeah, I know. I already shared this.
So are you able to click on that?
Yes, I'm able to click on that. I'm not able to see my slide now. Okay, now, but that's the wrong, that's the red form, right?
Okay, so now if you go at the bottom right, you see there is the 64% that says the zoom. Now, if you go a bit on the left, where you.
Yes.
So left, there it is. Click on that.
Yeah, but then I come into a new window. And this is not, I now see the presentation mode, but you don't, right?
No.
Yes. I mean, yeah, we still.
Could you maybe
So-
test and share again and share a new window that popped up?
And the problem is I can't start the presentation mode until I share the window, but as soon as I share the window, I cannot start the presentation mode. Maybe I share, that's the...
Otherwise, we go ahead and you just need to move slides.
Maybe now I see it. Yes, I think now it's possible. Now it's right.
Thank you. Yeah, great.
Okay, I switched to Apple. Maybe I have to switch back. Okay. So we have two planning tasks, and I have to be fast now. This international planning task, you see just an overview over like countries that will have a lot of excess energy in the future or already have, and countries that will need imports in the future. And from our German perspective, what we see is that Germany already started a lot of international partnerships on pilot projects. So our question was, how many of these partnerships make sense in the future to also have supply contracts, and with which partners should that be developed? We already heard a lot about long distance transportation, which might be a big issue regarding the costs. We already heard about the very high infrastructure investments that are needed. And we talked a little bit, but not too much, about the risks that might be involved in such big investments. And that was what we wanted to look at. So what we did, we scanned the literature on risks in energy systems, and there is a lot. And they use very different terminology and wording. And then we derived out of that 5 risk types: political risk, economic risk, natural hazard risk, dependency risk, and resource utilization risk. And you see all the underlying literature here. There is not too much yet on hydrogen. There's a lot on general energy systems. And what we then found out is that these are 2 different types of risks. We have, on one hand, supplier-specific risks, like political, natural hazard, and economic risks. And for these, we can find risk characteristics for single countries or for specific regions. And we can look into the literature. That there is literature from the World Bank, there is the World Risk Index or Global Competitiveness Index. And from that, we can find information on these different risk types and can really characterize the different countries with these risks. But then we also have network-specific risks, like resource utilization, overall resource utilization over all our suppliers, and dependency risk from not a high number of suppliers, for instance, which I think we learned in Europe, or especially in Germany 3 years ago, that dependency risk is not such a good thing. And these network-specific risks, we cannot really characterize a certain country or region with that, but these really depend on the supply network structure that we design. If you have a lot of supplying regions, the dependency risk is low. If we have only few regions, the dependency risk is high. So this is why the supplier-specific risk is an external risk for us. The network-specific risk is internal to our network and comes out as a result of our network design. What we did is we developed a B-objective optimization model, not only regarding hydrogen, but also hydrogen derivatives, other energy carriers that we already talked about today. And we have 2 objective functions. One is the typical cost or levelized cost function, and the other one is a risk index, which we derive out of that risk hierarchy that you just saw. We started off applying that to Africa, but the model is generic, so it can also be applied to the global scale. We collected a lot of data. We heard from Chalmers already that there's a lot of data behind these models. It's also like here, a lot of information about renewable supply, PV and wind power availability, country-specific risk index, transportation costs, production costs, and so on. And this is an Africa model, and I think it should hold to every part of the world. We have a very, very important requirement, which is fulfill internal future energy demand first, before there is anything going into export. Yeah. And then we analyze our results, and what we see is we have like here such a Pareto curve. We have a cost minimal solution, we have a risk minimal solution. We cannot have ideally both, but the risk reduction comes at a certain cost, and the cost reduction comes at a certain risk. And what we see is that the cost minimal solution is what we, I think, currently do in investments. We really focus on the North African part, because there is low cost transportation. But we also see that there is some risk minimal solution here, which is spreading investments over the African continent. But that comes at very high risk. But what would be interesting maybe is this very compromised solution here, where we can really reduce the risk a lot, but only have to spend a little bit more on costs. And I think this is a very interesting solution. We gave different weights. So we gave a high weight, for instance, to political hazards. We gave high weights to natural hazards. And then we could look at the different solutions and come out with some recommendations here. And what's interesting also is looking at the risk structure. So we see that there's a lot of economic risk, and there is also a lot of like political risk when we go for a cost minimal only solution. So that was our international supply model, and we are working on that still because we want to extend that to a global scale. And then we looked at our national hydrogen network. We just got this nice talk from Tim. And that was also what we were interested in. How could the national hydrogen pipeline infrastructure look like? What we need is we need hydrogen to fuel our economy, the industries. We need efficient transportation via pipelines, but we also might need storage because we have this fluctuating energy supply. And we have already a gas network, which we might be able to repurpose in certain parts, but maybe not fully. Maybe you have to build new hydrogen pipelines additionally. So what we developed here is a geographical information system based model. It's again optimization model with a heuristic that is looking for ideal pipeline pathways, not only like the Steiner tree that Tim presented, looking for minimal spanning tree in already existing pipeline, but also for the option to build new pipelines if necessary. So I think it's something in between the Steiner tree model of Tim and the engineering simulation model from the aggregation, something in between. And we look at seasonal storage options here. We again collect a lot of data on the production of hydrogen, on potential import flows from the sea, but also from hydrogen backbones from other countries, and demand of industries. And we also looked at potential storage options in caverns. For instance, we saw that already this morning that this is might be an important topic in the future. So what we did in our methodology, we developed a very, very granular geographic information system of Germany with a 1 times 1 kilometer pixel size regarding for slopes, motorways, national parks, rivers, lakes, population density, and also for existing gas pipelines. And then we kind of evaluated, I gave a threshold to every single of these pixels. So if there's already a gas pipeline, it has a positive value. And if it has like a national park, it gets a negative value in the evaluation. And then we have a heuristic that is finding its way through Germany, avoiding highly populated pixels, for instance, and looking for existing gas pipeline pixels. And with that, we can model future pipeline and also pipeline development over time. You see a solution for 2030, 2050. And what we did a lot was a scenario analysis, varying the future demand, because we learned from Catherine just that there is no commitment to hydrogen demand already, and that's really a big topic when we talk about such big investments. But what we can find with such pipeline models is we can find robust solutions that already in 2030 need a certain investment, and where we are really sure that even with a low hydrogen demand, we could start investing and start this pipeline infrastructure or repurposing of the gas pipeline infrastructure. And we already also looked at the storage options by varying the seasonality of production, of hydrogen production, increasing the importance of seasonality, cutting out seasonality from our model. And what we found is that the storage, the cavern pipeline solutions have nearly no impact on the network, because there are enough caverns or storage options that are near to the pipelines that are necessary to connect production and demand. And that was for examples of two models that we developed here in the hydrogen field. In the future, we will include like further supply countries in our risk index evaluation. We might look at more objectives like land use and water use that we also heard here already. Consider more uncertainties. Social acceptance is a big topic that we want to tackle. And maybe we are thinking about coupling the supply and transportation model in the future. It's all going back to two projects, the High Potential project, where we have a collaboration with Science Tokyo, looking at hydrogen economy in Germany and Japan, with a lot of very motivated PhD students, DFG funded project, and our excellence cluster, the Fuel Science Center, where we are responsible for the intersectoral and system analysis, also funded by our national research foundations. Okay, and with that, I thank you very much for your attention. Looking forward for
thanks a lot.
questions.
And you're on time, even you have problems with in the beginning. So I think there is no questions yet in the chat, but maybe there will pop up questions during the next speaker. So just look at the Q&A and answer questions later if they pops up, and then we move forward to.
Sorry, Selma, there is one question.
There is one. That's perfect. Yeah. When we take it. So yes,
some question on the construction of the risk index. So we collected all that risk information, and then for every single risk we have a different unit in the beginning, because some of the risks we might be able to measure in like events per 100,000 inhabitants or whatever. For some of the risks, we might only get like a linguistic variable, very high or very low. So we collect the data for the single risk. There might be even 3 data sources with 3 different units, but we have to merge them into one risk indicator. And in the end, we normalized every single risk type between 0 and 1. To be able to merge them to one risk index, and then we weighted the different risks. In the beginning, the first results that you saw were equal weighting between all the risks, and then especially regarding the current geopolitical situation, we gave rather high risk to the geopolitical situation, and then also tested for other weightings.
Thanks a lot for explaining that.